So we're going to have to wait for the talk. So I'll give you Thore Kockerols and MacroModelling.jl.
Yeah, so thanks everyone. Thanks for having me. Very excited to be here to present some work which I started during the pandemic and now came to fruition, and happy to present it here. So let me try to enlighten you. So I work at a central bank, so this is about models of the economy and working with models of the economy. And so what is MacroModelling.jl? It is a tool to make it easy, essentially, to work with models of the economy. Typically, they're called DSGE, dynamic, stochastic, general equilibrium models. But like if you're more from the engineering perspective, so this is stochastic control problems in discrete time and infinite horizon. So that's what we're solving. I mean, I didn't test it on those applications, but I mean, you can probably have a go at it. What questions can you answer with this? So you can do with this kind of model and with this toolbox, so you can do what-if analysis, scenario analysis. You get the model's view on the data, try to interpret it. Or you, from an academic perspective, you want to understand a specific mechanism, how a tax works, or those kind of things, and understand its effect. How does a typical workflow look like? I mean, you start by writing out your model, then usually, I mean, you iterate 1 million times over the equations and so on until you find something you like. You calibrate it, you estimate it, and then you do your policy experiments with it, and you try to explain the data, essentially. So this is what you would typically do. Who's the target audience? I mean, for now it's you guys, but it's typically people working at a central bank, regulators, academics in general, graduate students usually, who will look at this at one point. So why should you use this? Well, for one, you want to work with these kind of models, but then this toolbox specifically, speed, right? That's what we are all here for. Julia is about speed. Yeah, the code is fast. I wrote some custom gradients in there, which helps, especially with estimation. If you think about working with these models and the workflow, like speed in terms of execution time matters for the estimation part. That's where like the heavy computation is, and that's what you want to be fast. So there, the custom gradients help. And then, I mean, I'm standing on the shoulders of giants here. You can use the whole infrastructure which is there in Julia, the smart codes about estimation, gradient-based samplers, and so on. This is where this is fast. The other component, which I think, in my opinion, is even more important, is coding time. That's where speed matters a lot as well. So writing your models and convenience. So this, since I'm a user as well of these models, I try to take the perspective of like, what is the annoying part I want to do away with? And you spend a lot of time essentially prototyping, testing different equations in your model, and that I try to make as fast as possible via a few tricks. So for example, usually you define an equation, but then you have to declare variables. This you do not have to do here. So I use macros, which take away all this burden for you. You have to, in these kind of models, I'll explain it later, there's usually a steady state, which you have to derive. Usually you do that by hand, I mean, on paper. But also this is solved for most cases here. And this essentially, whenever you change equations in your model and so on, this is usually the task you need to do, but this is taken care of here. So this really simplifies your life a lot. It's a user-friendly syntax, so there's a domain-specific language here, which I set up, which also helps you. And sort of the benchmark, or the software which has been the longest around, was written in the 90s, Dinair. So that's where most of the code base of these kind of models is currently. That there are functions to import those models as well. So the cost of switching is relatively low. What is the standout functionality really of macromodeling compared to all the other universe of packages out there? So one is derivatives. I mean, it's not something which I invented and I claim that I invented, but here it's just the ease of having the derivatives available. So especially for sensitivity analysis, for any statistics you're computing. They're just easily available out there, which helps in your workflow and understanding how the model works, how the parameters influence certain things. The other things I talked about earlier, so the gradient-based samplers, you can use that, the optimizers using gradients. So this, combined with the convenience of defining the models, enables you to use these tools in combination with a range of models which are just there for you and easy to implement and to use. And last but not least, so for the optimizers, or if you estimate the model, I mean you can use all the data, but also only on moments. So there I devised some smart algorithms to chunk up the covariance matrix so you can do higher order moment matching. And last but not least, it's tested on 17 models, so it's tested against the industry benchmark that these results are sort of robust and the same as with the other software you would use. Now, speed. So speed is two things here, really. It's on the one hand, it's the custom gradient. I mean, that's what you need, and then it's also the sampler. So Turing no U-turn sampler, that's what helps. So here I took an example estimating a canonical model in economics, has 36 parameters, estimated over 40-something years with 7 observables. And there I compare sort of the industry standard, Dynair with MacroModelling.jl, and you see that using the no U-turn sampler, MacroModelling can do it in 15 minutes, and also the estimates are fairly robust, like you get a max R hat on any of these 36 parameters of 101, which is something where you can say, okay, I can go with this. Whereas with Dynair, like here it's estimating 2 chains of 200,000 draws, which takes around 40 minutes on the same machine, and also the estimates are worse. So it takes longer and you get worse estimates. So this is a clear gain. So that's where it makes sense to work with this. I mean, I'm not talking, or well, on top using the no U-turn sampler, which is not my doing, but in general I would recommend it. It's just more robust, right? In terms of starting points, like you have multimodal distributions which you're trying to estimate. I think that is a clear gain here.
So you're getting better results with less data?
No, not less data.
I'm saying number of draws is 1,000 compared to 200.
Yeah. So this is high quality draws.
Okay.
Yeah. Okay, so maybe some of you are not economists, so I'll try to enlighten you what we do. So with these kind of models, think of them as stochastic control problems, which means you set up an optimization problem. So you have, in this simple example, you have households and firms. They maximize something. So for the households, it's their utility. They maximize their consumption. For firms, it's their profits. That's what they maximize. And then they have constraints. So the households, they have a budget constraint. And then also there's capital in this model. For the firms, they produce, they have a production function, so some technology to produce. And they want to maximize the production, minimize the cost. So this is how you would set up the problem. We work then with first order optimality conditions. So after some derivatives in algebra, you get a set of equations. So these 6 equations here, essentially, that is what you use in describing the dynamics of the model. So this is a typical setup we use in economics. But as I said, I mean, this can be thought of as more general as a stochastic control problem. How do you code this up? So these 6 equations, like I substituted out 2 more, so you get these 4 equations here. And you can essentially translate it more or less one-to-one into macro modeling. I mean, that's the fun with Julia as well, right? You can use beta, the symbol, and so on. But it is very close to the mathematical notation here. And this is an example where I code up the model. So first I declare the equations, which are more or less one-to-one what you see above. Then I use a second macro for parameters to give him the parameter values. And then I say plot. And that's it. And in the background, he takes care of everything, essentially. He solves the model and gives me the output there on the right. So that is the solved problem, and that is sort of the level of convenience I was trying to get at, and that I think should make it clear that this is relatively easy to work with. But solving the model, right? So what does that mean? Also, I'll try to explain what I mean by this. So here we have these set of equations we're working with, right? It's 4 equations, but we have 9 unknowns. So this thing doesn't really help me in getting from, it's not a state space model, right? So I need to solve this so that I get to a state space representation. Now you can think of these 4 equations more generally as an expression of, well, it's a function of variables in the future, the present and the past, and then u is essentially the stochastic component of these 4 variables, c, k, q, and z, which I have. And I'm looking for a state space representation, which just brings me from yesterday to today. So that means solving the model. Now, what you usually do, typically, in these kind of settings, you take a perturbation solution, linear. So this is sort of the first best guess, which you use typically for these models. So how does that work? Well, perturbation solution means you take a Taylor series expansion around a point, which point you take the non-stochastic steady state, or deterministic steady state, if you like. So what is that? That means that, so this model had a stochastic component, that one becomes deterministic, as in 0. And the other variables, so they're at steady state, they're not moving anymore, so they're just stable. So we're solving for this expression there with the y bars and the zeros. That's what we want to have, and that is relatively easy to do. And then we do a Taylor series expansion around this point. So we take the derivatives of the function at this point, and that is fairly easy to do in Julia. We get 4 different matrices with derivatives for the future, present, past, and the exogenous shocks, and then we try to bring it into this state space representation. Now this will be, in this case, would also be linear, so we're trying to bring these 4 matrices into 2 with some substitution in there. You get to the bottom matrix quadratic equation. That's what you need to solve. That's all in the linear algebra. That's fine. This is standardized. Like there's not much magic to do. So the magic actually happens before, from like bringing the equations to these matrices, essentially. And that is usually the hard part, and that is what is made easy here. Now, the non-stochastic steady state, that is the point around which you do the perturbation, right? So this thing was actually the first motivation why I started working on this, because it's painful and I just wanted to get rid of it. I think I managed. Well, how did I manage? So the non-stochastic steady state, so here on the left are still this is the system of equations with the 4 equations and 9 unknowns. But then, since I'm looking for the non-stochastic steady state, I can reduce it because there's no more timing. They're all time invariant, and the exogenous component also disappears. So this becomes an exactly identified system that I can solve. But it's a nonlinear system of equations, and that is hard. So how do I go about it? There are some smart tricks which you can use. Also something I didn't mention here, I added an additional calibration equation where I just want some steady state relationships to help here, so that is the 5th equation there. So everything here with the sort of subscript infinity means that's the steady state. But then I can use on the right-hand side, I can use some tricks. So first, I can eliminate redundant variables. So here the c doesn't really matter in the first equation. I can partition this into independent blocks. The blue equation with the z's, I can solve that independent of the other equations. So separate the problem out. Then what I do is, like, I attempt symbolic solution using SymPy under the hood. That can work well. It definitely helps. Sometimes you can also just simplify just some parts, not solving it fully, but only partially. It definitely speeds up the computations. Then the next part is, so you have some domain constraint terms because of the way you set up this problem. or the problem is set up. So if you look at k, for example, here, it's to the power of of alpha. So k can only be positive. And so this you can infer from these equations that okay, this one is only defined on a specific domain. You can use that information, and in the background here, I introduce auxiliary variables, which then are domain constraints, so that the solver doesn't run into nans and just errors out. Because that is the next step. I wrote a custom system of nonlinear equation solver, which is of Levenberg-Marquardt type, which then uses box constraints in order to not run into the log of -1, essentially. It has domain transformation as well, which I found also very useful. If you take the hyperbolic sign and you just transform the whole problem into something more narrow, that also helps. And then essentially, if all of these steps they don't work, I use brute force, and I and then I just take a simulated annealing over the parameter space of the solver and the initial the starting points, and just let him go, and that gives you a fairly high success rate in solving these models and saves you a lot of coding time. And last but not least, okay, so given that you solved it, then there's a set of predefined parameters which are optimized over the 70 models implemented there. And then you just pick the one which solves this problem the fastest way. So you try, try to solve it. Can you? Okay, yes, you can. And then let's make it fast. So that's sort of what I'm trying to do here. Now, the domain-specific language. So this is thanks to the macros in Julia. This is really powerful. Now, I introduced it briefly before, but here just some other points of things which happen in the background. So these variable definitions. So here, for example, C, which is consumption, like the square brackets and 0, this is the timing subscript. So 0 is the present. But you can put there 2, 20, -15, whatever you want. But if you do that, then the model definition was only past, present, and future. -20 is like 20 times in the past. You need auxiliary variables. So you augment the state space. This happens in the background here. Which is usually a very tedious job to write this down. You can use programmatic model writing. So there's some for loops here where I define shock processes of 2 kinds. Also, I define a Q, which is GDP annual. So I go over the 4 time periods. So this helps you in setting up your problem. Calibration equations. So automatically finding sort of the parameters here. I want to know the alpha such that the capital to output ratio is such and such. So this I can write down in this way that it becomes part of this finding the steady state problem, and he takes care of that. The order of parameter definitions is irrelevant. Like he figures it out. Like I use capital to output ratio before I defined it, but he'll figure out like, yeah, I actually need this, so I put it first, so he understands it. And it parses expressions, right? So not only numerical values here, I put 1/2. So all of these things is taken care of thanks to the macros of Julia, essentially, which is a lot of convenience of things which usually you don't, which has nothing to do with the modeling, but then you run into these roadblocks and you're losing time on it. So how does it compare? I mean, and this is just to say, like, compared to the industry standard, like where do we stand here? Here's the model definition on the left. I would write it down in MacroModelling. Okay, and the industry standard, usually Danair, works like this, that first you have to define the variables, so you have to declare them, which doesn't happen on the left. Then you write the parameter definitions and the model equations, which are the same, minus the nice syntax with the alphas and betas and so on. You have to define the shocks as well, which you don't need on the left. And then this is the crucial part. You need to give him some information about the steady state, some initial value, some equation, something that he can figure it out. Like otherwise he won't figure it out. And then it's script based. You have to tell him what he wants to do. You have to run the script each time. Okay. But when you work with these models, especially the steady state, and you think about modifying it, sorry, modifying it, that's where really you get the gains in the coding time. Because let's add a shock and see how this plays out in the two scenarios here. So here, essentially, I had delta, which is the depreciation, which before was a parameter, and now I make it a process which is driven exogenously. So I have one more equation here. I have a few more parameters defining the exogenous process, and yeah, that's it. So I have to change here deltas, one more equation. That's it, what I have to do in macromodeling. If I do that in Diner, well, I have to change the variable declarations. So delta used to be a parameter, now it's a variable. I have to introduce the new variables in there. Equations and parameter definitions, okay, that's the same. Now I have a new shock, I have to add the new shock. The initial values, I have to add the new initial value because there's a new variable. And this is a simple example. If you have a more complicated example where you even need to write a function to find your steady state, you have to take care of that in all those places. And that is where, if you just want to simply check something, the coding time is just way faster if you do it like this. Now, working with a model, that's another thing. I mean, it's a simple thing. This is the plot I showed you here on the left. Any of the functions, essentially you have a parameter argument, and you can just plug in new parameter values, and he will find the steady state, solve the model, and will give you the updated plot. So in your workflow, you can just change the parameters, and by simply typing plot IRF and the parameters, okay, let them be different now, you get the different solution, which again, in your workflow, helps you tremendously in trying to understand what the metal does, how it behaves, and so on. So there's, again, convenience. Now, another thing, which is one of the sort of standout features, I would say, sensitivity analysis. Also here, this is about, like, I have a model, I want to understand how it works, how do the parameters matter in my model, so I can calculate statistics. So here I took two statistics. I took the non-stochastic steady state, which I want to know, and also the standard deviation, theoretical standard deviations of my model variables, okay, of my state space variable. But also I want to do this at third order. So I do not only a first, that's 5? Okay. Not only a first order perturbation solution, but I do a third order perturbation solution. This I can do by simply defining, like, somewhere in the script that the algorithm should be third order. He will then go on, take the symbolic derivatives up to third order, and solve the model up to third order. But I don't have to take care of all of this. But the real thing what I wanted to talk about here is the derivatives. So here, thanks to the infrastructure with regards to derivatives, I mean, again, didn't invent them, but just make it available, you can see sort of not only the steady state, but then also how the steady state changes for different parameter values. And not only for the relatively simple problem of the steady state, but also through the whole solution of the nonlinear systems of equations and linear system of equations. Also, for example, for these objects such as the standard deviations. So then you really understand, okay, which parameters matters for the variable I'm looking at. So this, I think, is a great tool for exploring and understanding the model. And essentially, these derivatives, plus the fact that I can, with any of these functions, I can just write comma parameter should be something else. I can really explore this parameter space relatively fast because I understand in which direction I'm going, and then I can just change it and look at that. So this is also very convenient. Now, last but not least, so I'm not the only and not the first one who looked at this kind of model. So here's a bit of a rundown of what you have, the whole universe. So I put MATLAB. Well, actually, so I put, it's 2000 first public release in MATLAB. It was actually released earlier in 1994 or something in Gauss, I think. So that's really the dinosaur. MacroModelling is a bit the new kid on the block. There's also some other packages in Julia. Sort of the oldest ones are DSGE.jl and solve.dsge.jl. And then more recently, differentiable state space models. and state space econ. So how does that compare? So I think I talked about the non-stochastic steady state solver. That is really a standout feature here compared to the others. Automatic declaration, that is, yeah, I'm the only one who provides this, which I think is very neat. The derivatives with regards to parameters, yeah, I have it, but also differentiable state space models has it, but it's more about the fact like how easily available is it. And in general, then there are some sort of computational things which you usually want to have, like what perturbation order, do you use pruning, what about occasionally binding constraints, so nonlinearities, where some parts I have, some I don't. But I think another important thing here also to note is timing convention. So as I said, Linear is the industry standard, has end of period timing. So most of the models are written in that way. So I think it's important also to be compatible with that, which is actually, yeah, there's one more other package which has that. And the fact that you can write the model within your script, like you don't have to write a separate script. I find this very convenient to have it in your normal workflow. Compared to a separate script. So this is the package. Where do I want to go with this? So this is also an invitation to anybody who's into these kind of things. I'm very happy to collaborate. So I want to continue working on the graded-based estimation, but of the nonlinear model solution. So for now, it's only the linear model solution. So also bring that to second, third order perturbation. It's about taking gradients, essentially. A generalized global solution method, I think that is a big undertaking, but worthwhile and very interesting, I think. Specifically neural networks, I think, are useful there or promising. Balanced growth path. So, I mean, usually there's a single attractor if you do the linear solution. If you have balanced growth path, you can have a line as an attractor, but you need to handle this. Then sort of right now, I said it's a stochastic control problem. Why don't we define it at that level already? Why do we have to go to the first order conditions and then work with these equations? We can start even earlier because it's only taking derivatives that the computer can do. So that could make it even more convenient. And last but not least, but that is also a big leap, is heterogeneous agent models. So I forgot to say, but all of these equations you've seen is mostly representative agents. And with this, I conclude.
All right. Yeah, thanks for the great talk. Let's see. There we go. So we can go to questions now. Should have a few minutes for that. And actually, we're going into lunch right after this. So if you have questions, you can, beyond that, you can all hang out here and keep asking. So any
I have a 20-minute conversation, but that's later. It's very interesting. Very interesting.
If you want a question over there? We've got a microphone coming.
I will come for the mic. Okay, so this was great, but I have another I have another question. How does this compare to dinar.gl? Because I understand dinar is somehow being rewritten to Julia, and I think it's financed by the Central Bank of France or something like that. And because you've been, so how is the performance, and do you have any experience with that?
Yeah. So Linear.jl, so I didn't put it here. So Linear first released 1994, 2000 MATLAB. In Julia, I think it was March 2022. They have a subset of the features they have in MATLAB, essentially. So it's by far not feature complete. If you then are looking for speed, as I was trying to say earlier, like the speed gain there wasn't an entirely fair comparison, right? Because it was two different samplers in a sense with their own characteristics. But Linear.jl doesn't have the gradients yet. So you wouldn't be able to use the no U-turn sampler. I mean, they use sequential Monte Carlo. So in that sense, you wouldn't, in the part which matters, which I argue, estimation, you wouldn't get that. Yeah.
More questions?
In terms of sampling speed, if you just, I'm assuming you took the raw default setting of Dynair for the random walk Metropolis Hastings, but then a lot of the times we would send it to an RA to tune the hyperparameters. How does the speed comparison look if you hand tune the parameter of random walk Metropolis Hastings?
Okay.
Sure, throw an easy question.
The charm with the no U-turn sampler is that you don't need to do that. So here it's really about, yeah, it's like a, whatever, you take a blind shot and the thing will hit the target, you know it. So that's the coding time, right? So by the time you hand-tuned your Metropolis Hastings sampler, like days are gone, whereas this thing churned through in 15 minutes and you know it's something robust. So I think that's the main part. Sure, in the end, by the time you tuned it, and you adapted the code to the problem and so on, yeah, it might be faster, but you spend the time in between as well. So I think...
But then, so the one you have is the default setting of Dynair?
Well, it's the standard setting which comes with a replication package. Yeah.
Hey, do you have a way to easily convert models from other, let's say, packages like a jump, for example, if you build your model in jump with the constraints or with the parameters, do you have a way to convert it from that framework onto yours in an easy way?
So you mean take a jump model and bring it...
yeah, like I imagine there are many, like the objects more or less kind of similar, right? In terms of like having, you have an object, you have some constraints, you have something.
Yeah.
Is that something you have or plan to do? Or
No,
make or something?
okay, so no, that's not what I have. I've seen a discourse thread where they go through different ways of solving these type of models, where I think also they have it in jump. I think you would be, like, you could, in that direction of compatibility, you could do it for sure. I mean, given the macros, you have whatever, infinite ways. But I think in the, question would be a bit why, like if you have that model and you want to go to this because you want to use the functionality, okay, yeah, I see why. But otherwise I would argue, okay, but start with the convenience provided here already.
Yeah, but it's more like if you're already building a framework in Jump, let's say, and you want to have some of the features that are available in, like, for example, the sensitivity analysis that is available here, and what would be like a nice way to have like an automatic way to convert models.
Yeah, no, well, I didn't think about it. I'm not keen to hear what you have in mind, as in the specific models, but yeah.
Oh well, I think it's possible, or I don't think it would take a long time to implement. So that's why I was wondering if you already had it. So because it's also like a macro, what's it called? It seems like it's very similar way to build models in terms of like how you with the macros and stuff.
Yeah, no, the starting point, sure. Then, like down the line, there's different parts, but yeah.
Okay.
But not yet. But I'll add it to the Outlook to-do list.
Nice.
Okay. Officially, I believe this is time for lunch. If you have more questions, I'm sure you can catch Thore at some point here today. Thank you for the great talk. And